Good morning, good afternoon, and welcome to those who may be joining us on our recording. My name is Stephanie Lewis. I will serve as your moderator today. Before we get started with our formal presentation, I would like to give you a little bit of an overview of the NICR webcast series, as well as tell you how to navigate within Teams. A list of all of our recorded and webinars that are open for registration are available on the NICR website. Any links provided throughout today's slides are clickable, so feel free to click on any of those links. Just a quick note, you are in a listen-only mode, which means you will not be able to speak to us directly, so you don't have access to your camera or your microphone. But you can submit any number of questions or comments throughout today's presentation by utilizing the chat and or Q&A feature. We will be monitoring both. Feel free to view the list of those that are logged in by clicking the attendees list, as well as give us some applause or thumbs up or some giggles throughout today's presentation by utilizing the chat feature, or excuse me, the react feature. If you experience any technical difficulties throughout today's presentation, there is a telephone number that is associated with this call. Please feel free to click on the three dots for more. Go down to audio settings and you can have Microsoft Teams call you. And at the end of today's webinar, simply click the leave button to exit our webinar. So with that being said, it is my pleasure to introduce Dr. Yvette Cruzado from the University of Puerto Rico, Mayagüez. She serves as a professor within the Department of Civil Engineering and Surveying at the University of Puerto Rico, Mayagüez. Dr. Cruzado has diverse her research interests to encompass areas such as public transportation, big data, incident management using aerial unmanned systems, highway safety, and engineering education. With that, it is my pleasure to introduce Yvette. So Yvette, take it away.
Okay, thank you very much, Stephanie. I hope everybody's doing okay. I'm going to try to do the best to put all the information that I have together and try to summarize it in a very efficient time manner. But the title of our presentation today is exploring the use on unmanned aerial vehicles or drones for traffic management, the validation of algorithms, methodologies, and insights. I want to show you who were the research team for the third year of the project. This is a research project that took 3 years. And from the Department of Civil Engineering, we have the professors Alberto Figueroa and Didier Valdez. From the Department of Industrial Engineering, my statistics guide, Dr. David Gonzalez. And the way we had for the last year, we have 3 students working with us. Luz Rivera, she graduated, she obtained her master's degree graduation last May. Brian Ruiz is still a graduate student doing his master's. And we have an undergraduate student also in civil engineering, Josue Diega. So today, what we're going to do, let's do a little bit of introduction and background. I want to show you what we did on the previous 2 years of our research, the objectives for the third year and the methodology that we follow, and then the good part, the data set and the descriptive statistics, followed by conclusions and recommendations, and then we'll have our Q&A session. So let's do some introduction and background. Well, we all know congestion. The NICR, this is part of NICR, the National Institute for Congestion Reduction. What are we going to do about congestion? Vehicles, demand exceeds capacity, but sometimes we have other conditions that can lead to congestion, like traffic incidents, work zone, adverse weather, and physical bottlenecks. Our research was about traffic incidents. How can we manage congestion during those? And according to the Federal Highway Administration, we have 3 types of traffic flow breakdowns, which are bunching due to reduced speed, intended interruption of flow, and vehicle merging maneuvers. So the idea is, how am I going to use the latest technology and try to use it to manage congestion and to reduce it. And we focused on the use of drones. And we found one in our literature review, one of how have drones been used lately. And it goes back to the first drone. What they used was like a military balloon. I think it was 1849 in the picture. And then it started being used, the use of drones started to grow. And I believe it was 2010 with Katrina hurricane. That's when they started using drones for a lot of various conditions. So here we can see the usage and the growth of drones. You can divide them by commercial use or recreational use. The one in the commercial use has been slowly growing, where you can see that the number of drones registered are much, much higher than the commercial ones. And this is in the United States, and also that happens globally. Now, how can we use the drones? And based on a survey that they did for the Department of Transportations, by then, 39 out of the 50 states of the United States, they use drones daily. They are mostly used for bridge inspections. That would be 53% of total inspections. And they are used for other things like roadway conditions and structural inspections. In Puerto Rico, I'm afraid they are not being used that much, at least not as much as I want. So let's try to concentrate a little bit in that, how we're going to be using the drones. And I think this one is better in the next slide. And you can see, okay, how we can use drones for surveying, data collection, study, surveillance, research, and inspections. And on your graph to your left, you can see that the highest distribution goes to the inspections, 42%. Out of those inspections, like I previously said, bridge inspections take 53%. Other commercials are using for doing inspections on solar panels, other structurals, high mass poles, the airports, rock fallings, and roadway conditions. I will mostly want to do roadway conditions. I would like to see that percentage of inspections of roadway conditions to increase, but that's just me and I'm biased. So this is basically what we're all thinking for the last 3 years of our research project. And we started very slow, I will say. Like, okay, the first year, how I'm going to use drones for the inspection of roadway conditions or incident management. And one of the things is that there was no protocol. There was nothing to tell, okay, so what guidelines are you using? Nothing. So, okay, so our main objective in the first year of the research was, well, let's develop a protocol to use drones for traffic incident management. And, the students were very happy because they get to use the drones and they had to study and they had to take the exam, the pilot exam, and they all passed, thank God. But on the other side, we were partnering with USF, and USF they were already collecting data and flying drones. We were not that lucky. We had to start. We were very behind them. So USF was developing a background subtraction algorithm to identify vehicles. So while we're doing the protocol and we're taking the exams and we start collecting data, we'll send that data, those videos that we'll take it to our USF fellows so they can run the background subtraction algorithm. And this part, I think, is very important because if you have been to Puerto Rico, you'll notice that we're not flat like Florida. We try to have these very nice freeways, but it doesn't always work like that because we have this very mountains, a lot of mountains, and we have a lot of vertical and horizontal curves. So at the end, we have the same goal that it was, how are we going to integrate the use of drones in real-time incident detection to assist in reducing congestion and delay? In One of the outcomes for the first year with the protocols were the use of tables. This is an example of one of the tables, like, okay, what are you going to do before using the drone, before the flight, during the flight, and after the flight? And this is just an example of the tables that we developed. This is for before the flight. Like, what are you going to do? You have to, these are like kind of checklists. You have to make sure that you have the credentials, that you clear the airspace, that you evaluated the area, the weather conditions. You need to have an emergency plan, the flight plan, and you have to inspect the drone. And we did that for during and after the flight as well. And we started collecting data, and this is when all the, when you start actually doing the data collection, that's when you start saying like, oh, we're going to have this problem. Oh, are we going to have this problem? And this is just an example of one of our places where we were collecting data. This is a freeway. It's in a mountain. It has, you can see there are two horizontal curves. And this was the first day of data collection. And actually, while the students were collecting the data, there was an incident. There was a little fender bender, I think you guys call it. And they were like, oh, an incident happened. And they tried to fly the drones over there, but they noticed that because it was one of the first times using the drones, that the default values of the drones did not let them go that far away. And they also noticed that because of the mountains and the horizontal curve, it was not very easy to how are we going to take the drone over there, because you have to have the pilot and the visual observer, and the visual observer could not longer see the drone unless they move to another location. So this is the kind of things that we all started collecting data on. Besides the actual collecting data with videos of cars, it was also collecting the data of the things that were happening. For the second year, now we have all this data. Now we have the background subtraction algorithm, and we want to analyze the background subtraction algorithm from our partners at USAF, because again, the conditions in Puerto Rico are different from the conditions in Florida. So we started by collecting data, field data, videos at different elevations of the drone and distance from the side of the road. And it's very important that I tell you that this data for the second year was all stationary. The drone will be deployed to a certain elevation, and it will stay there collecting, taking videos of the cars as they pass by. And as they were collecting the data, they were doing several activities, and they will, again, evidence everything from these activities. They will be polishing the protocol used before, and they will reinvent it, and they will write down how will you perform activities. They did like 7 activities. What if I'm going to use this kind of filters? What if I'm going to use 2 drones to collect data at 2 different sites, 2 different elevations, same place? This one in particular, activity 2, I wanted to show it to you because we used that protocol about 3 months ago for another research project that we're doing. And it's like, how am I going to use 2 drones, at least 2 drones, to collect data for at least 1 hour? And we have the problems that the drones, they do not have batteries that last for an hour. So the more that they can do, but to do 15-minute videos. So they had to deploy 1 drone, make sure, learn how long it will take to get to the specific location or elevation, make sure when it had to come down, the moment the other drone will have to go up to be probably almost in the exact location without colliding, of course. And this is the protocol that they developed for that research, for that activity. And one of the things that we learned for the research for the second year of the research was the drone elevation. We started doing like 100 feet, the drone elevation, 100 feet, 200 feet, 300 feet. 100 feet does not work because we had problems of occlusion. Like you can see in the slide, there is a truck that is covering another car. And if we want to use the videos to identify vehicles, some of the vehicles are not going to be seen. So what did we learn from year 2? Number 1, the positioning the drone closer to the road is associated with higher percentage of vehicles. That was the distance from the road, but not the drone not on top of the roadway. We have 2 different types of drones. One of them did better at a higher elevation, while the other thing happened, the opposite happened to the other drone. It did better at lower elevations. And we saw that some of the factors that can be responsible for when the background subtraction algorithm was not able to identify vehicles will be in high traffic densities. Sometimes the color of the vehicle will blend with the pavement and instructions on the roadway. And this is how we get to our 3rd year. Our 3rd year, we are looking back at our previous 2 years, okay, and we're still on the main purpose. How am I going to use drones for traffic incident management? And mostly, how I can I use them to replace what the road rangers do in the field. So now we're going to collect data, but the drone is not going to be stationary. The drone for the 3rd year was going to be moving data. Because that's the advantage of the drones. If I want to do stationary data, then I can just put a bunch of cameras along the highway, along the freeway. But the drone, the advantage is that it can move. So now we're going to use it, and now we're going to use the pre-planned feature of the drone, and that is that you tell the drone exactly. Nobody's going to collect. Nobody is actually flying the drone. You tell the drone, okay, this is the route that you are going to cover, and then you're going to come back. And we are going to now also validate a detection algorithm, but no longer the background subtraction algorithm. We use YOLO 7. So this was our methodology. Of course, we always start with a literature review. And then I think we became a little bit, what's the word? We wanted to do a little bit more and said, let's see if we can do sites. We can collect sites that we already know that there are hotspots. There are a lot of incidents over there. And that will be our identification of sites. Then we'll have to learn how to do the pre-planned flights on each drone that we have, collect the data. And then just like in the 2nd year, we're going to see how good is a drone at detecting vehicles. So for the identification of sites, we use the Puerto Rico Road Safety Observatory platform. This is not a platform that is open for everyone, but we were able to have access to it. And you can select different roads, and it will tell you the number of incidents per year, per 5 years, or something like that. And we don't have a lot of freeways in Puerto Rico. So we try to concentrate on freeway number 52 that goes from Ponce, that is in the south coast of Puerto Rico, all the way to the metro area in the north. And based on the red spots, we could see where are the location of the hot spots. And then we use Google Street View to check out the conditions, but we ended up having to do field visits because we have a criteria for these sites. We wanted to be with a lot of incidents, but we needed to have, it had to have clear space for flying the drone. But the students that will be collecting the data, they had to be located someplace that they are safe. And there were so many roads, there were so many sites that we wanted to use along Road 52. This particular in kilometer 14.5, there were having 274 crashes in the last 5 years. Now, most of those crashes are just property damage only. But it was too close to an airport, a military zone, or something like that. This one was good, by the way. I'm sorry. But the sites, a lot of the sites that were very good, we had to exclude because they were on a no-fly zone. Like, for example, if they were not in a no-fly zone, we will have a problem, and is that we will have no place where to locate the pilots and the visual observers when flying the drones. And these two sites were excluded for those reasons, because there's a lot of, 3 lanes, big shoulder, but right after the shoulder, you can see there's the guide rail, and both of them actually, and there was just no place where we could be located. And that was a bummer. And this is, my idea will be in the future that every drone will be deployed by itself and do the pre-planned flights. What we did was, okay, we're going to collect videos while the drone is moving, but we're also going to take advantage of it, and we're going to collect both moving data and stationary data. Each drone has their instructions for pre-planned flights, and basically you select the waypoints, you select where the elevation, and exactly this is, you're going to going first from this point to this other point at this speed. At this second point, you're going to keep collecting data, keep recording videos for this how many minutes, move to the next one, and like that. And we develop also protocols, or like a kind of like a guideline how to use that. And basically, let me jump back one moment. I don't think I see it here. Yes. Okay. So as I was telling you before, I'm sorry, we didn't have a lot of sites to include in the freeway PR52, the one that runs from Ponce to Caguas and vice versa. But on PR number 2 in San Germán, this is an example. It is basically a multi-lane, but there are some sections that can be viewed as freeways. And we're thinking, okay, no, we're running out of time, good enough. And there is a place where the students can be located while piloting and observing the drones. So we're going to do field activities, and we did the site inspection, the data collection. Okay, we decided on a site on PR52 and also this one in San Germán. And we're going to do, based on our previous research from year 2, we're not even going to bother with either 100 feet of the drone elevation or 400 feet. That's too far away. We only did 2 elevations, 200 and 300 feet. These are the characteristics of our 2 sites. Remember, PR52 is actually the freeway. They had 4 legs because there were 5 waypoints. Let me show it to you. I'll be back to the other one. If you can see, there are basically 5 waypoints that are the yellow on the they're very looked. You can see them better on the picture to your right. The 5 yellow points. That each one of them is a waypoint. So you end up with 4 legs or segments, and each segment was between 500 and 600 feet. For the site in Caguas, we have northbound, southbound, and we also have a dynamic toll lane, that is the DTL. The posted speed limit was 55 miles per hour, and it basically was this plus, we did it in level terrain. And the same in San Germán, but San Germán, there's no DTL. It runs eastbound to westbound, and it has 2 lanes per direction. And the speed limit is 55 as well. We ended up doing 3 activities of data collection. One on the Caguas site, and then when we collect the data on a peak hour, they do in the PM hours, or during 2 weekdays, they took 8 minutes of video time collection. At each waypoint, they will collect data, stationary data, for 1 minute. And they basically did the same thing in San Germán another day of the week. And then they returned to the Caguas side to try to collect data as well, because they wanted also to see if we were able to obtain traffic data from the traffic management center near Caguas. And we wanted to use that, but we were not able to actually have access to that data. We collected the data. We have the videos. We're going to run the videos through the YOLO 7 algorithm to see how good is at identifying vehicles. But we have to validate it, and we have to validate it with manual counts. So we have to go frame by frame, somebody manually counting how many vehicles were actually there in the per frame. And we have not only counting the vehicles, because the algorithm will tell you per frame, I'm counting this many vehicles, but sometimes the algorithm counts something as a vehicle that is not a vehicle, or a vehicle is counted twice, or a vehicle is not counted at all. Sometimes appears in one frame, sometimes not. This part took a lot of time. This is where we spend a lot of time doing this. I'm not going to lie to you. So the summary of the methodology, we did, we did the site selection process. We collected data, different elevations and different distance from the road. Let's see how good it is, the drone or the algorithm, depending on drone, elevation, distance from the road. And the idea is, insights for improving traffic management and safety. Now, let's get to the good part, the data set and the descriptive statistics. For those who like statistics, this is where it all comes. We're going to use because we had video data 2 times from the Caguas site, we decided to use that for our validation of the algorithm. Not that we didn't use the site in San Germán. We also saw a lot of interesting things, but I don't have 3 hours to do for this webinar. So we're going to concentrate only on the site for Caguas. We have 2 days of data collection. And we said, okay, so basically we have 2 replicas. We were wrong, by the way. We collected data on December 21st and February 3rd. The environmental conditions were sunny skies, dry pavement. It was the start of the actual afternoon peak hour. Okay, it looks like we're going to do good. And we're going to evaluate the YOLO 7 algorithm efficiency in detecting vehicles, from these videos captured by the drones. So only 2 elevations, 200 feet and 300 feet. We have 4 legs because we have 5 waypoints. And we run it through the YOLO 7 algorithm. Okay. This is when we have a little bit of, okay, how are we going to evaluate the efficiency? Because sometimes, as I mentioned before, the algorithm will detect something as a vehicle. As you can see here in the video, that is the starting, they're approaching a toll plaza, and there is an exit to your right for those ones that are traveling to the right. So sometimes that barrier, it will count it as a vehicle. But it did identify all the vehicles correctly. We have the object detected by the algorithm on the table. And frame number 1 was 8. There were actually, this is just an example of tables and tables and tables of data collection. The algorithm detected 8 objects and identified them as vehicles. But the person verifying that frame, see, there were only 2 vehicles in the frame. So there were 6 non-vehicles detections. The non-vehicle detections will be the objects incorrectly identified as vehicles. And we did that frame by frame by frame. I believe it was 30, I think it was 30 frames per second or something like that. I'm not sure now, so I'll get back to you. And what we did, we had an issue. These ones are different days, and we actually have a difference in traffic conditions from one day to the another one. So sometimes, we actually saw that we have issues with vehicles, more errors where traffic was dense. And this, if you see on the right video, sometimes because the urban location, that neighborhood to the north of the video to your right, you can see that there's some parked vehicles, but they are still in the side of the drone, so the drone will identify them as vehicle. That is true. I mean, there are vehicles, but they are not actually on the road. So it's stuff like that we have to see and, validate the algorithm. That took a lot of time. So just so you can see some of the descriptive statistics for the videos. For the first replica, day 1 or day 2, and I put replica in red because that was our intention, that would be replicas, but the traffic conditions were different. So basically, there were no replicas. Replicas are supposed to say everything stays the same. So we have to, use them, see them as day 1, as day 2. For the first day, or replica 1, the manual counts is the actual number of vehicles per frame. On average, will be 58, in the 50s for the elevation of 200. No, for hotel, and then the DGI was between 80. And this is different. This is the same elevation, by the way. But for the second day, replica 2, the number of vehicles were smaller. They range between 14 and 22 vehicles per frame. And you can see the objects detected by the algorithm were always a little bit higher. On average, they were always a little bit higher than the manual counts, except for maybe on the second day at an elevation of 200 with the DGI. Manual counts were, on average, were 20, and object detected were 19. And you can see the number of non-vehicle detections. That is that objects are identified as vehicles by the algorithm on the last 2 columns. Now, if I'm interested in seeing how good the drone is detecting vehicles, well, actually it was pretty good. I mean, it detected all the vehicles in the frame, but sometimes detected more. So we have problems. We have some kind of error. Yes, there were, I'm going to show you this first because these are the instances where the number of objects detected by the drone equals the number of real vehicles, or the manual counts too, in the first row, plus the objects that were incorrectly identified vehicles by the algorithm. So 2 plus 6 is 8. Okay, alrighty. And what is the percentage of vehicle detected? 100%. But that was, so we have this error. We have non-vehicle detections could be seen as an error of the algorithm. But that was not only the case. Sometimes we have vehicles that were not detected and vehicles that were detected twice. So we came up with, okay, what are our A/B errors? And for example, if positive, it means that it detected one vehicle twice, or if negative, yes, it was a negative, it missed a vehicle. Let's see first row. There were 86 objects detected and identified as vehicles by the algorithm. That's the 86. But there were really 75 vehicles. So 86 minus 75 is 11. Out of those 11, non-vehicle detections, there were 10. Okay, Now I got confused here. This is the part where it gets a little bit confused. So the manual counts, there was one vehicle that was counted twice. And that was the number one. Yes, that's how it is. Let's do, I know it's a little bit confusing. So let's see the third row, the 83. There were really 75 vehicles. The object identified 10 of those 10 objects were identified as vehicles. So there were supposed to be 85 at the end, but no, object detected were only 83. So 2 vehicles were missing. So now I have this type of error. Missing vehicles not counted by the algorithm, and vehicles counted twice. And I'm trying to find out, again, how do I measure the efficiency of the drone? So we did, okay, so we have total errors. Those will be the non-vehicle detections plus the absolute value of the AB errors. And then we did the percentage efficiency will be 1 minus the total errors divided by the manual counts per times 100. And that's what we did for every single frame. And we have some statistics. Let me show them to you here. Okay, here we can see the total errors and the percentage efficiency. So for the first day, we have more errors compared to the second day, the total errors, but the percentage efficiency is higher. On the first day, we have the highest is 88. However, the second high, 88%. That will be on day 1, elevation 200 with the outtail drone. And then we have an 85% in the last row, 85% of efficiency. That will be on day number 2 at 300 feet with the DJI drone. So, I mean, if you like data and all these, curiosity things, I think that's pretty awesome. Okay, so we wanted to do, in our proposal, we said that we were going to run an ANOVA just like in the second year to see what are the factors that influence my efficiency of the algorithm. I only want to use the drone elevation, the replica, and the drone type. We actually kept the drone at the same distance. But ANOVA has some assumptions that you have to meet. And one of them is independence. Now we have over 20,000 frames or observations that are correlated because they are taken in time, very close in time. So we reduce our data set to run an ANOVA. And we ended up from 20-something thousand observations, we went down all to 160 observations. And we did that, and all these observations are random. And these are the descriptive statistics for that reduced data set. In the 4th column to your left, you'll see that the number of them, we basically have 20 observations per elevation, drone, and day or replica. And we observe again the manual counts, verify everything, okay, we're good. And we're going to do the ANOVA, and we're like, I don't think we're going to be able to meet the assumption of almost elasticity or equal variances. And we saw that we can see here, this is the box plot of total errors by replica, drone type, and elevation. And we also did this by percentage efficiency. And then the second day, both drones, both elevations, they look, they look pretty similar. But the first day, it was so different. Remember, the first day is where there's a lot of traffic congestion. And we're like, I don't think we're going to meet that assumption. So, we knew what was going to happen. Still, we ran the bonus and the Levine test to verify. And yes, test says, no, you do not meet the assumption of equal variances. But, not everything is lost. Okay, so ANOVA is not appropriate to study the influence of drone elevation and the drone type. But even if the ANOVA was not performed as we originally want to, the results of these tests are, we consider that they are significant because this suggests that the algorithm is influenced by traffic conditions. So with them, I had the conclusions and recommendations. On our key findings, traditional methods like manual patrolling of the highways for incident detection, like we do in Puerto Rico, we do believe they're not efficient or effective in these scenarios. If there is an incident and there's a lot of congestion, it's going to take a lot of time for the patroller to get there. And sometimes what happens, if you have that first fender bender, then you can have a second fender bender and not even notice because everything is already congested. So, but we do believe that using drones seems like a promising alternative to offer real-time video data collection. It would be awesome if, we did collected videos, we downloaded them, then we saw them, but it would just be awesome if those videos will be directly sent or transmitted to a traffic management center. We accessed the Puerto Rico Road Safety Observatory platform, which I'm not going to lie to you, it was very cool to use. We were able to, and we selected the sites, we checked them out with Google Street View, but still we had to go over there, the field visits, and see that most of our sites that we wanted to use, we couldn't because of safety reasons. We were able to, evaluate the YOLO 7 algorithm for the vehicle detection from the drones. It looks like, yes, elevation, drone type, and traffic conditions, especially traffic conditions, influence the efficiency of the drone. And we highlighted the need for adaptive algorithms using tool. Yes, again, the most important thing for me will be the efficiency, the influence of the traffic conditions on the algorithm. That means that you will have to train the algorithm for various traffic conditions. But, maybe with the use of AI, this doesn't have to take a lot of times. These are our recommendations for future research to optimize algorithm for variable traffic conditions. We really want to use the drones for traffic management systems, and again, explore artificial intelligence for improved detection accuracy. And I feel like I talk too fast, but that's what I have for you today. I'm going to let Stephanie take control again.
Yes, absolutely. Thank you so much for all of the great information and sharing that project with us. I'm going to skip to the end. If anybody has any questions or comments, feel free to drop them in the chat window for us utilizing the Microsoft Teams. It does look like we had several questions that came in during the registration process, so we'll go ahead and ask those first. It says, what was the biggest challenge in collecting the data?
I will say the biggest challenge was because of our position in Mayagüez. So Puerto Rico is small, but it can look like everything is very far away. And we are on the West Coast, and we have no freeways on the West Coast. So we have 2 students to collect data and a third one for visual observer. They're taking classes in the meantime, and it's good to take data during weekdays. That's what we need to do. So find a time where everybody's available. That's a challenge Then they have to drive more than 2 hours for the site, except for the one in San Germán. That's another thing. That's why we chose that site, because it was closer to us. And safety. Oh, and the clear space, because maybe it's so little, but then you have a little airport here. I mean, Puerto Rico is small. We have a little airport here, a little airport here, a little airport here, and then it's just like, oh, we don't have size. There's this many places when we can collect data, but because of clear space restrictions, we cannot do it. I would say that would be data collection. That would be it.
Great, thank you. And what was the biggest challenge in analyzing the data?
Oh, 30, I saw it later in one of the slides, 30 frames per second. It was months of the students looking at this video one by one and doing manual counts. I don't know how they still have their eyes. Sorry. Oh, I would say manual counts. That took so much time.
Tedious. Sounds very tedious. Very tedious. Okay, and then the final question that came in was, in your opinion, how can drones be used efficiently for incident management?
Oh, okay. This is I get to talk about my dream. Okay. Drones, incident management, you never know what's going to happen unless, it's a work zone or something like that. But a crash or something, or somebody with a flat tire or running out of gas, you don't know when that's going to happen. And you cannot have patrolling officers everywhere. I would love, in my dream in the future, you have all these drones in this battery location, in these stations, and they can recharge the batteries, solar, by the way, using solar panels, and they would they will patrol by themselves. With the use of pre-planned flights, just let the drone, patrol the area, check everything, and send that video, real-time video, transmitted to the traffic management center. Maybe the algorithm, I'm getting too excited now. Maybe the algorithm can see the difference in traffic congestion and said, okay, this is not the peak AM or peak hour, something else happened. And because traffic management, then you have to have a lot of people looking at all these cameras. So maybe you could have like a little emergency button or something like that, a notification. Okay, look at me, look at the drone now. I have something important to tell you. Okay, that will be it.
Great. Here comes a question. It says, since beginning the project, has any of the newer image recognition AI software been considered or implemented?
For either incorporation into the algorithm for the vetting to spur the students' eyes. It looked like we were going to do this one. I think we're going to do YOLO 6. And by the time we did our literature review, then already YOLO 7 had applied. It looked, in terms of the algorithm, it looks like they were developing faster than we could work. But for the eyes AI, no, the answer is no. We did not consider any AI software to spur the student's eye. Now I feel very guilty, by the way. Thank you.
Maybe if you were to redo it again or a different version, you can think about how AI can. Yeah, it says, I suppose the follow-up is you'll consider this for future iterations. So yeah,
yes.
AI may play an important role in the future research.
Yeah, we ran, and we went into a no-code extension. So actually, when we all did all that, it was lots of months ago. We actually ran into a 1-year no-code extension on the project. Achilles.
Yeah, Achilles says you still have to validate the ground truth.
That is true.
Yeah, true. Okay.
That is true. Yeah, we're always going to have some poor student on his eyes.
Yeah. All right, doesn't look like we have any other questions. The evaluation is on your screen, so you can simply scan that QR code and or click on the link. The the information provided in that evaluation is really important to us. And then just one final note, we do have another NICR webcast scheduled for August 1st, Transit Prioritized Vehicle Scheduling at General Conflict Area under Connected and Automated Environment. So again, that link is clickable on the screen, take you directly to the NICR website. So again, on behalf of the National Institute for Congestion Reduction, thank you so much for joining us this afternoon or watching on today's recording, and we'll see you all real soon. Bye, everybody.
Thank you. And thank you, Achilles.